Good day, everyone. My name is Nur Alia Fadlina, and today I will present my project on dengue fever transmission using the SVEIR model. My presentation is divided into 8 parts, starting with the introduction and ending with the limitations and future work. Dengue fever is transmitted by Aedes mosquitoes. Since transmission involves both humans and mosquitoes, mathematical modeling can help simulate how dengue spreads over time. The problem is that dengue transmission is affected by many factors, including vaccine coverage, vaccine efficacy, infected mosquitoes, and vector control. This project focused on these factors in an interactive simulation. This study has 3 objectives. The first one is to formulate the dengue model. The second one is to develop a MATLAB app designer interface. And the third one is to analyze the impact of vaccine coverage on dengue transmission. This project supports SDG 3 through dengue prevention and SDG 9 through mathematical modeling and digital simulation innovation. Previous studies show that vaccination effectiveness depends on both vaccine efficacy and coverage. They also suggest that combined control strategies are more effective than single strategies. This slide shows the main variables and parameters used in the model for both human and mosquito populations. This project used a quantitative simulation-based approach. The human population is divided into susceptible, vaccinated, exposed, infected, and recovered groups, while mosquitoes are divided into susceptible, exposed, and infected groups. These equations describe how humans and mosquitoes move between compartments over time based on infection, recovery, vaccination, and vector control. The system of differential equations is solved using the fourth-order Ranskata method, or RK4, because the model contains nonlinear interaction between humans and mosquitoes. The basic reproduction number, R0, is used to measure dengue transmission potential. A lower R0 means a lower chance of dengue spreading. The graphical user interface follows this flow, starting from parameter input, running the simulation, displaying graphs, and showing the risk indicator. This is the completed MATLAB app designer interface. Users can adjust initial conditions, vaccine coverage, vaccine efficacy, vector control, and simulation settings. The interface displays several outputs, including human dynamics, mosquito dynamics, intervention comparison, heat map, R0 comparison, and risk color indicator. The simulation used these default values, including 80% vaccine coverage, 80% vaccine efficacy, and 50% vector control effectiveness. For human dynamics, susceptible humans decrease over time, while exposed and infected humans rise and peak around day 75 to 80. Recovered humans increase continuously. For mosquito dynamics, susceptible mosquitoes decrease sharply. Exposed and infected mosquitoes remain low, showing that vector control reduced the mosquito population effectively. Comparing intervention strategies, no control gives the highest and earliest infection peak. Vaccination and vector control reduce infection, but the combined strategy gives the lowest peak. Vaccination clearly reduced the number of infected humans. It also delays the infection peak from around day 38 to day 59, showing slower dengue transmission. The sensitivity analysis shows that as vaccine coverage increased, the peak number of infected humans decreased. Therefore, higher coverage gives stronger infection reduction. The heat map shows that infection reduction improves when both vaccine coverage and vaccine efficacy increase. The best results occurs when both are high. For R0 analysis, no control gives the highest value. Vaccination and vector control reduce R0, while the combined strategy gives the lowest value. For serotype comparison, serotype 2 shows a higher and earlier infection peak, while serotype 1 gives a lower and later peak due to different vaccine effectiveness. The key result shows that vaccination reduced infection by 34.81%, vector control by 19.03%, and the combined strategy by 55.34%. Therefore, the best strategy is vaccination with vector control. The dengue risk indicator gives a moderate transmission risk with a score of 65.5 out of 100. This means dengue is reduced but still needs monitoring. In conclusion, this project successfully developed a dengue transmission simulation using the SVEIR model for humans and SEI model for mosquitoes. The results show that vaccination reduces and delays infection, especially when combined with vector control. The main limitations are fixed parameter values, no real dengue case data, simplified serotype comparison, and no vaccine waning. Future work can include real data, seasonal factors, all for serotypes, and spatial analysis. Thank you for listening.